Good morning, everyone, and thank you for joining us today. My name is Alma Ahmed, and I'm part of the student network team, and I will be hosting this webinar today. So, as usual, the webinar is going to last for about an hour, and at the end, we will have time for some questions. So, because you're also all muted, if you do have any questions, please feel free to type them in the question box, and I will run through them at the end of the presentation. So our presenter for today is Emma Beswick, and the webinar is entitled Nutrigenomics, Why Context is Key. Emma is a qualified nutritional therapist and a band member. Her interest in nutrigenomics was sparked by a lecture on the subject while studying nutritional therapy at CNM. After researching and experiencing many DNA tests on the market, she was inspired to create LifeCode GX to provide ethical nutrigenomics testing, analyzing and training for clinical use. LifeCode GX training includes webinars, seminars, and new for 2019, a nutrigenomics retreat. All training is band CPD accredited. So in this webinar, Emma will discuss some of the most common mistakes and the opportunities for nutritional therapists to support their clients by providing nutrigenomics expertise in the context of nutritional therapy program. I just had a quick chat with Emma, and I'm really excited to learn more about nutrigenomics because I find it such a confusing subject. So without further ado, it is my pleasure to introduce to you our presenter. Emma, please welcome.
Thank you, Alma. And thank you for inviting me to do this webinar. As Alma said, I am the CEO of LifeCode GX. It is my company, and I set that up when I was still studying, actually at CNM. So we were ready to launch by the time I graduated, which is just over 3 years ago. And we try to unravel the mysteries of nutrigenomics and see it from a practitioner perspective. And that is really one of the key differences between how we work and how a lot of other companies work. We are very, very much practitioner focused. So there are my details. I'm not going to say too much more about that, other than you can see more information on our website and our social media, and you can sign up as a student practitioner with us as well and get all the same benefits as a full practitioner. The information about how to do that is there. Okay, so we're going to talk about briefly what nutrigenomics is, why someone would do a test and how they would do a test, and then focus on how to use it in practice and look at individual gene examples, some connected genes and test panels, and then also the considerations around practitioner support and client support as well. So very briefly, why do a genetic test? So a lot of direct-to-consumer tests are oriented around ancestry, and that's really where they started. So they look at what percentage of a certain ethnic background or group someone comes from, and some of them also look at health. But because they're driven from the ancestry perspective, quite often the health aspects are fairly wanting and limited, although that is changing slightly. Most of those direct-to-consumer tests are fairly light. The other reasons are investigation to find the root cause of a problem, prevention, if there is a family history of a certain genetically linked condition. For example, someone might want to dig deeper into that and try and control for their own risk in the future. And then finally, optimization. So there is a lot of buzz at the moment around longevity and growing old healthily, and also being performant both physically and mentally as long as possible into old age and throughout life. So these are all reasons to do a genetic test, but probably 2, 3, and 4 are the reasons that we would, as practitioners, be most interested in for our clients. So genetic testing basically looks at the the genome. It can look at the whole genome or part of the genome. That genome is basically billions of pairs of letters that make up DNA. So they're called base pairs, and they're organised in little groups of 3, which are codons. They code for amino acids, and those codons are chunked together to make proteins, or genes that code for the proteins. And those genes are organised on 23 pairs of chromosomes. So that's really the structure of DNA. So at the lowest level, it's the alleles, or the bases. They come in pairs. They are grouped into strings of 3, which are the codons, which are again grouped into genes or proteins, and then the chromosomes are the 23 pairs, and the genome is the whole thing. So most DNA test companies still at the moment look at genotyping, which is a selection of the possible genome base pairs that they could look at. That's really for practical reasons, because it is still quite expensive to do whole genome sequencing. And it's also quite overwhelming as well to deal with the amount of data that would come back from a whole genome sequencing exercise, and you wouldn't know what most of it meant either. So most companies do this selective genotyping. They all approach it in a similar way. So you get a sample through blood, saliva, or cheek cells. That is taken to the lab. It is extracted, so the DNA is extracted from that sample, then it's sequenced, and you get some little letters come out at the end, which we will show you now. So this is typically the raw data that comes from a genetic test. On the left, we've got the reference sequence, and this is important because it's the unique identifier of the point in the genome that you're examining. So it's the confident way of knowing exactly what you're talking about, and that's the official reference for that point of data. It also usually shows a chromosome, a location on a chromosome, which is a count from one end of it, and then the genotype, which are the 2 bases or the base pairs. So you inherit one of these from each parent. So at the top there, we have an A and a G, and the A would have been inherited from one parent, and that is probably the default letter. But this person has inherited a G, which is the variance, the alternate letter from the other parent. So when someone has an A and a G, or a C and a T, so the combination of 2 letters, that's known as heterozygous. So it's like the halfway variant, whereas if it's 2 letters that are varied, it's called homozygous, and if no letters are varied, it's called wild. So that's the genotype. So this is a bit of a busy slide, but it shows the impact of a variant. So this is what we're looking for. We're looking for changes to the genome compared to a default genome. And that change could be to a single letter, it could be to a whole sequence within a gene that could be missing, or it could be present, or it could be copied, duplicated. It could apply to the whole gene. So we do have examples where a whole gene is missing, for example, or a chromosome where you have maybe a 3 copies of a chromosome, as in Down syndrome, rather than 2. And these changes can change the function of a gene. So there's a little example here where we can see that in green, in the square box, we have the letter G, and that is part of a codon, so part of a sequence of 3 letters that codes for tryptophan, TRP, the amino acid. So that is the default wild type. But if that G is changed to an A, it actually changes the codon, so that rather than coding for the amino acid tryptophan, it actually codes for a stop. So that's like a full stop in the sentence or the gene. So the impact of that is to curtail the gene and stop it part way through. And as you would imagine, that changes the shape of the protein that the gene codes for and therefore its function. So you would expect in this situation the gene to function differently to the wild type if it's a completely different shape to normal. And that's just the impact of one letter changing. However, all SNPs are not equal in effect or magnitude. So on each gene, you can have tens of thousands of potential SNPs because you've got thousands of these letters strung together. And a lot of those can change, but they might not change the amino acid because there are multiple ways of coding for some amino acids, or they might change the amino acid, but it doesn't have any overall impact on the gene. So one of the important things to remember is when you're looking at SNPs, look for the ones that are well evidenced and well understood. So some tests and some tools will report reams and reams of SNPs and just big lists of them showing that they're varied, but that doesn't actually mean they have an impact. It just means that the letter is different. So I believe, and my colleagues believe, that that isn't useful. It can actually cloud the picture by making people think they've got more variance and therefore more effect when that isn't necessarily the case. So we focus on the SNPs that are known about and understood in terms of the effect and the magnitude or potential magnitude of that change of effect. So we take the raw data, which you've seen, and at LifeCode we have a database where we curate lots and lots of research where we've identified the impacts of those variants, and then we basically press the button and generate a report which is an interpretation of that data, and we interpret it from a nutrition profession perspective, from a functional medicine perspective, and it's really, really important that this information is considered in context, which is the title of this webinar, and hopefully that will become clear as we progress. So there are different ways of interpreting a test, and on the left there I'm showing you the actual base pairs in the result. So we talked about wild type being no change, so this is the most common way of reporting it. It's usually reported as green because it is usually the most beneficial version. Sometimes it's reported as minus, which means, I guess, no change, no change. I personally find that a little bit confusing still and often have to look it up again. The next one is heterozygous, where there is one letter change. That is often reported as amber because it is often detrimental or potentially detrimental in terms of impact to some extent, and that can be reported as minus plus. So one letter not changed, one letter changed. And then finally homozygous, which is a double variant where both letters are the variant, the alternative, and that is often reported as red because it usually reduces the gene activity or alters it in a negative way. But at LifeCode, we use colour coding to actually represent the impact of that change so that you can look through the reports and see at a glance, these are the ones where there is a negative impact and therefore may need attention. I think the most important message here is that whatever test you're using, make sure that you read the key and that you understand what these colours mean and what these symbols mean, and that you're interpreting it correctly as the test company or tool intended, because it isn't consistent. So this is what it would look like in one of our reports. So we would show, in this case, the VKORC gene is a gene that affects vitamin K recycling, and therefore the vitamin K status, and one of the effects of that is the stickiness or the clotting ability of blood. We show the variant and the specific reference sequence ID, so it's totally transparent, you know exactly what is being talked about or represented. The genotype, which in this case is homozygous, and is red because it's perceived to be negative, because the impact of this is to reduce the efficiency by which someone recycles vitamin K, and that can reduce the overall vitamin K status and impacts blood coagulation, bone health, etc. And then we put a statement there which is designed to help you know what you can do to support that person. But we'll also provide information about the bigger picture as well, things to look out for, like bruising or bleeding easily, are all symptoms of vitamin K deficiency as well. So just a quick review of the key things so far. So there isn't a standard way of reporting, so make sure you do understand what that report is telling you, and don't assume that they're all the same. Don't assume that red is bad, for example, because it might just mean that it's different. And then secondly, that all SNPs are not equal. And again, if you get a big report with lots and lots of SNPs on the same gene, some of those SNPs won't have any effect and some will have a massive potential effect. And that more data isn't necessarily better. You've got to believe and know that that data is relevant and be able to see the wood for the trees. And then whether a SNP is good or bad may depend on the context. So just because it is varied, it doesn't mean it's bad. And we've actually got some examples of a SNP being positive and helpful in some contexts. So a little overview of how genetic testing fits in the functional medicine model. And this is what I was taught when I studied nutritional therapy as well. So we have antecedents, triggers, and mediators, and the genetics are the antecedents. They're what you're born with, they are you. And then the trigger for health impacts is usually environmental, and then mediators are a combination of both the genetics and the environment interacting with each other. And the word for this is epigenetics. So literally epi for over and genetics. So the environment acting over the genes. And you can see in the functional medicine tree on the right hand side there that genetic predisposition is right at the heart of that, but we need to look at genetics alongside the signs and symptoms, the lifestyle, environmental factors, the diet, etc., and all the systems analysis and family history that we would do usually. And it's important to think of it that way and not try and use genetics as a quick fix and a quick answer. It should be looked at in that context of the bigger picture. And if you want any convincing about how genomics fits into the functional medicine model, I would recommend that you look at these two books. The textbook of functional medicine is quite old. I think there might be a more recent one than that, but it's still totally relevant. And genetics and genomics and nutrigenomics are just littered through both of these books, and I would recommend both of them if you want to understand that and to read and use genomics in the right way. Okay, a little bit of terminology. So nutrigenetics, nutrigenomics, the two terms are often used interchangeably, but they are slightly different. And so nutrigenetics is about the effect of gene variation on dietary response, and nutrigenomics is the role of nutrients in gene expression and how that affects gene expression. And we've got some examples here. So nutrigenetics, these genes on the left affect a person's response to certain nutrients. So we're going to look in detail at some of these, but the ones that we're not going to look in detail at, HLA, DQA1 and DQB1, these are two genes that affect people's response to gluten, and there are variances that have to be present in order for someone to actually develop celiac disease. So those variances give the potential, they're the antecedent for someone to develop celiac disease. And then there's a very lovely gene called clock that I absolutely adore, that because it sounds like what it does. So it is affected by light, and it triggers circadian rhythm and resets our circadian rhythm in response to light, ideally in the morning. So there are some nutrigenetics examples. And nutrigenomics is about the effect of nutrients on our genes. So we're going to look in detail at methylation and how certain methyl nutrients affect our genes. We're also going to look at how cruciferous vegetables help CYP450 genes and detoxification. But there are a couple of others, like grapefruit can slow down a CYP1B1 gene, which means that we can adjust the amount of potentially damaging estrogen that someone synthesizes by introducing grapefruit into their diet. But of course, we would also have to consider potential contraindications with medication. And then at the bottom there, smoking, which some people do still smoke, actually increases the expression of a gene called CYP1A2, which is the gene that metabolizes caffeine. So this is something of an explanation as to why in some cultures, smoking and caffeine drinking go together, because people can actually tolerate more caffeine if they're smoking at the same time, because that's helping to metabolize the caffeine more quickly. So that's just to demonstrate the meaning of those terms, but oftentimes it's used interchangeably. So let's get down to some examples. This is an example of a gene, the LCT gene, or lactase gene, which converts lactose to galactose and glucose. Now, normally, this gene is switched off after weaning. So when people are 2 or 3, naturally, the gene becomes inactive and people are no longer lactose tolerant. Now, that's the ancestral global default position. The majority of the world population experience that. However, if there is a variance on this gene, or more accurately, a gene further upstream, this affects the way that the lactose gene is expressed and enables it to continue being expressed. So that means that those people can continue to digest lactose for their whole life. And this has evolved, so the theory has it, as long as farming has developed. So that's why it also varies according to ethnicity. So 66% of Caucasians, roughly, have the variant, and the idea being that Caucasian populations started to farm animals and started to drink dairy, and gradually that gene became more prevalent and the dominant gene in those ethnic groups, so they were able to benefit from drinking milk from cows and sheep, etc. But only 2% of Asians have that variant, so most Asians can't drink lactose or digest lactose as adults, so they'll get all the kind of all the symptoms of gut dysbiosis associated with that. So this is an example of a positive variant, so a gene that is perceived at least to have a positive effect, because it means that people can continue to digest milk. And certainly historically that would have been positive in terms of survival and thriving and even becoming an adult. So all SNPs are not negative, they can have a positive implication. The other thing is, this isn't necessarily totally black and white. So people with the wild type may be able to tolerate a very small amount of lactose, but most of the time it's pretty clear that they're not tolerating it. And I've experienced so many results where people have had no idea that lactose is the problem that is behind the bloating and dysbiosis until they've seen their gene result, and then the penny is dropped that is why. Okay, so moving on to vitamin A. This is a more typical scenario whereby a gene variant can be negative. So the BCA1 gene is needed to convert beta carotene to retinol, and then that becomes retinol. And we all know that vitamin A is needed for eyesight, etc. Now, if people have a variant on that BCA1 gene and they eat a large amount of beta carotene, it can actually turn them orange, and that's because the BCA1 gene isn't working as quickly as it might do, and it's not converting that beta carotene, so the beta carotene is building up in the system. So it can also affect the white of your eyes, so people might confuse it with liver problems, when it's actually just people eating a lot of beta carotene to the extent that the body can't convert it. So this is what vitamin A does in the body, and some symptoms of deficiency or insufficiency. So light blindness, but also susceptibility to infections and thyroid disorders and skin disorders. So there are actually two SNPs on the BCA1 gene that are known as R267S and A379V. These are alternate names to the reference sequence numbers that we discussed. So oftentimes these names represent the codon and which number codon the variant occurs in, and they're easier to remember than just an RS and then a long stream of numbers. So that's what they mean. And the frequencies of these again are quite common. So 42% and 24% of people have these variants, and they can have a combined impact of up to 57%, which is quite big in terms of the effect on a gene. So what if people have these variants, then what can they do about it? So really it means they have a need for preformed vitamin A in the form of retinol, and that is mainly found in animal product foods. So the thing to consider mostly here is the context. Is the person presenting certain symptoms? So they might have these SNPs, but they might not be experiencing any symptoms, and that might be because they're doing everything right just by chance to support those SNPs anyway. So what is their nutrient intake? Are they taking in beta carotene? Because they can still convert some of that beta carotene. So we still want to make the most of the gene activity that is there. It's not a case of saying don't bother eating carrots or peppers or sweet potatoes. They are still very, very good for you. But does that person have lifestyle or nutrient restrictions or beliefs that mean they aren't obtaining preformed vitamin A or retinol? So for example, if they're vegan or vegetarian and they're not supplementing and they have this genetic variant, then they're probably more at risk of being insufficient in vitamin A, the active form. So it's a question of looking at the gene alongside that person's diet and behaviour and the symptoms that they're experiencing to decide if they need to do anything about it. So, for example, if someone is vegetarian and they have the gene variants, they might need to supplement in order to optimise their vitamin A status. But if someone is eating animal products, they might not need to do that at all. Okay, so another example, detoxification. We're going to look at glutathione, which is known as the master antioxidant. And this is really, really important for detoxifying lots and lots and lots of different things, but in particularly heavy metals, medication, hormones as well. And there are a number of genes that help or use glutathione for that purpose. One of those genes is called GSTM1. It's particularly important. And in this case, the whole gene can be absent. So it's not just one letter change or one letter missing or a little bit missing. It can be the whole gene. So as you can imagine, that would have a fairly significant effect. However, this is the case in a lot of people. So about 50% of Caucasians have an absent GSTM gene. So that means there's no activity on that gene. So if it was that important and that impactful, then those people wouldn't survive. So again, we need to look at the bigger picture and understand why people can exist and can be healthy if they have this GSTM1 gene, whereas some other people might not be healthy at all and might become really sensitive to chemicals. They might have lots of symptoms of heavy metal toxicity, for example. They might not be very good at detoxifying hormones. So it depends on the bigger picture. So these are the things that we would look at alongside the GSTM1 gene. So always, first of all, look at the starting point. So what is the exposure to toxic substances in the first place? Does that person have amalgam fillings? Have they got imbalances of various hormones, etc.? What symptoms are they presenting with? Do they get headaches, nausea, chemical sensitivity, so they can't stand certain smells, for example? And then also, what is their glutathione status? Do they eat sulfur foods? Are they getting cysteine, which is a precursor to glutathione? So we can make glutathione in the body. We can also get glutathione directly from certain foods like watermelon, for example. So is the person getting those nutrients in the first place? And then what other genes might be involved? So this is really important always to look at other genes. So the CTH gene and the GSS gene, for example, help the body make its own glutathione. So you would always look at those alongside GSTM1. You would also look at other genes in the GST family. So there are two genes, GST-T1 and TP1, which work alongside GSTM1, and the person may have missing genes across the board, or they might just have one missing and the others might be compensating for that. And then the other thing is antioxidant status in general, because vitamin C and E actually support glutathione and spare it and help it be recycled. So they're going to help support glutathione status as well. And then you can test. So I'm sure you've all heard the phrase test, don't guess. So if we've tested the genetics and you've discovered that someone has certain weaknesses and variants, you may then want to test functionally and look at the current status. So the genetics will tell you someone's predisposition, and that predisposition is for life, so the code will not change. But functional testing will tell you the person's status at that point in time. And it can be incredibly powerful to look at those two things alongside each other, to understand someone's vulnerabilities, but then also understand whether those vulnerabilities are actually materializing and happening, or whether you are managing to reduce that risk and offset it, and it isn't actually a problem at all for that person. So those are some of the things that you could test for in the context of detoxification and glutathione conjugation pathways. So moving on to vitamin D, and this is useful to explain the way that receptor genes work. So receptor genes are a little bit different to the ones that we've looked at so far. The genes that we've looked at so far are involved in converting a substance from one to another, whereas what receptor genes do is they affect a person's response or sensitivity to a certain substance. So the substance, such as vitamin D, interacts or binds to a receptor, and that triggers a whole lot of messages throughout the body to tell it to do various things. So it's that binding action between the substance, the nutrient, for example, and the receptor that makes all these things happen and triggers them. Now, if someone has a variant on a receptor, generally it will mean that receptor is less sensitive. So the person is a little bit deaf to the effects of that nutrient or that hormone or that neurotransmitter, for example. So we've got some other examples here, like serotonin, thyroid hormone, etc. And the principle is the same, that it's about how sensitive someone is. So for vitamin D, this is an example of putting two or more things together. So there is a transporter gene called GC, which helps transport vitamin D throughout the body. And then there is a vitamin D receptor gene that basically controls or affects our sensitivity to the vitamin D. And you can see here that via that VDR receptor, here are some of the effects that vitamin D has, or some of the functions. So very, very broad range of functions and very, very important functions. So you can see there on the second bullet point that vitamin D, or the vitamin D receptor, regulates several hundred genes. So it interacts with thyroid, it interacts with neurotransmitters, it interacts with the immune system, and also bone health. So very, very far-reaching effects just because of how vitamin D interacts with this one gene. So I'm going to stick to VDR for now and focus on that. There are actually 4 SNPs that are often looked at and analysed in the context of VDR, and they've all got different extents of effect. And you know, when I said all SNPs are not equal, this is an example of them not being equal. So the top 2 are also known as BSML and TACL, and they're the most impactful. So those are the ones that are most often reported. And these are some of the effects of either low vitamin D or the impact of having a vitamin D SNP. So this is the same thing. If someone has a VDR SNP and a less sensitive vitamin D receptor, that is ultimately a similar impact as if the person had low vitamin D in the first place. So the important thing to support these SNPs is to make sure that the person's vitamin D is optimal, and that you don't let it dip, because for them, having suboptimal levels is much, much more impactful and damaging to their health than it would be for someone who didn't have those SNPs. But you do have to be careful, because vitamin D can be toxic. So it's absolutely not right to say or make a judgment that just because someone has a vitamin D receptor SNP, they need big doses of vitamin D. It doesn't work that way. You can have too much of a good thing, and there is a limit to the effect of vitamin D. So you can put more and more in, but it will only have a benefit up to a point. So more is not necessarily better once it goes beyond a certain point. So as nutritional therapists, we would do the responsible thing and suggest that people are tested for vitamin D levels. Even if they've got a VDR SNP, we want to know what their levels are, but we want to try and optimise that. We don't just act on the back of a gene variant. So those are the fairly simple genes, or some examples of fairly simple genes that you can look at one at a time. And although we're talking about context and bigger picture, you can see what that gene does on its own in almost a one-step process. But now we're going to look at methylation, because you can't look at genetics and nutrigenomics without looking at methylation. So I'm just going to highlight some of the key points and some of the mistakes that people often make when they're talking about methylation. So first of all, people find methylation quite confusing and they find it difficult to describe. But basically what it is at a biochemical level is the addition of a methyl group, and that is a carbon and 3 hydrogens. So methylation is this little compound which is passed around from one substance to the next, thereby methylating it. And to do that, there are various compounds that donate the methyl group, such as methylfolate, trimethylglycine, and SAMe, or the long word is S-adenosyl L-methionine, but SAMe is known as the master methyl donor. So these all include the methyl groups, and they donate them to make various reactions happen. So very high level, this is the folate cycle and the methionine cycle. And what we're trying to do is take folate, convert it into methylfolate. Lots of genes are involved in that, and lots of nutrients are involved in that as well, which I'll come to. Then that methylfolate, which is the 5-MTHF at the bottom, is actually used to methylate B12. So this is the middle bit. It donates the methyl to B12, so that little methyl group's been handed over to B12, and then in turn B12 hands off that methyl group to homocysteine, and the homocysteine is converted to methionine, and then methionine is converted to SAMe. So the methyl group is just hopping around from methylfolate to B12 to homocysteine and helping make SAMe the master methyl donor. But you can see there are other nutrients and other genes involved in that. So let's have a little drill in. So at the top, or the first cycle, we've got folate coming in at the top there, and the folate goes through lots and lots of steps, which I'm not going to go through them all, to get to a penultimate substance called 5,10-methylene THF, and then that is converted by a gene called MTHFR, which I think everybody has heard of by now, to methylfolate. So the reason it gets so much attention is because that's the only way the body can make methylfolate, by that gene action. And the other reason it gets lots of attention is because it can be varied and have quite a big impact. So one variant, one particular one, which is known as C677T, can have up to 70% impact in terms of reducing that gene activity and reducing the rate of conversion to methylfolate. Now, the important thing here is to recognise that the words up to. So it doesn't necessarily mean that everybody with that double variant can only convert at about 30% of the rate as someone without the variant. It depends on how much folate they have, how many of the cofactors and the status of the cofactors that you can see in purple here. So B2, B3, B6, all really important for supporting this process and getting to the penultimate substance and then acting as cofactors for MTHFR. So it has been shown that having more folate and more cofactors can almost totally compensate for that variant. However, a lot of people think that people need methylfolate if they have a MTHFR SNP. And I would say hold that thought for the moment, because I don't believe that it is absolutely necessary, and you need to look at more things before you make that decision. So one thing that I'll show you here is that once we've got methylfolate, you can see there is an arrow going back round up to THF, which is tetrahydrofolate. And that's because the methylfolate is actually split and the folate bit is recycled back into the folate cycle, and then it goes back around all these arrows and cycles and different substances, and it needs the B6 and the B3 and the B2 for that to happen. So just giving someone methylfolate without the cofactors is going to limit the usefulness of that methylfolate. Certainly in terms of the recycling part of it, you need the cofactors as well. And that's why nature provides these vitamins all together. So the next step is the arrow goes over to the right, and as I said at the high level, it donates the methyl part of methylfolate to B12. But guess what? In order to do that, in order to split the methylfolate into the folate and the methyl, it needs B12. So if there's no B12 to pick up that methyl group and to hand it over to, then the methylfolate can't work. So it can't go anywhere and it can become trapped as methylfolate. So you might have heard of the methylfolate trap. And that means the folate can't go back through the cycle, and you might get symptoms of folate deficiency, like anemia, for example. And it's not because of lack of folate necessarily, but it's because the B12 isn't there to work with it. And that can also be impacted by a gene called MTR, which we're not going to go into too much detail here. But the important thing is it's not just about folate, it's also about B12. So B12 comes in lots of different forms, but we need B12, and there are genes that can affect the status of B12 or our ability to absorb B12 and transport B12 in the first place. So we need to look at these genes alongside the MTHFR gene and the MTRR gene in order to understand how these all interact. So these genes can affect someone's ability to get B12 in the first place, and then if there's not enough B12, that's going to limit the usability of methylfolate. Okay, so then the B12 hands over the methyl to methionine, and it is then demethylated. So the unmethylated B12 that you can see here needs to be remethylated, and that needs a gene called MTRR. So if you've got SNPs on MTRR, that can affect the ability to remethylate the B12, and that also needs zinc, and it needs SAMe itself as a cofactor. So if the whole methionine cycle is quite sluggish, that can mean this whole thing grinds to a bit of a halt. So again, you might consider methylated B12 as an option if you're thinking about supplementing, but you need to look at the MTRR gene, and you also need to look at the other cofactors. So the MTRR gene, if that is varied, it is generally slower. So that can mean that you're less able or less efficient at remethylating that B12, and you might consider methylcobalamin as a supplement if you are considering supplementation. Okay, and these are genes that all need methyl. So if methylation isn't happening efficiently, any gene that ends in the letters MT, so these are the short names for the genes, but that stands for methyltransferase. It means they need a methyl group as a cofactor. They need a methyl group to work. So if someone's methylation status is suboptimal, it can affect all these things. And this is just a really small list of genes that need methyl groups. There are hundreds of them. So if methylation is too low, then these things might work too slowly, and there might not be enough of them. Alternatively, if there is too much methyl, then some of these processes can get kind of geared up and they can work too quickly. And I'll come to an example of that in a second. But the point here is that methylation is fundamental to so many other actions and functions in the body. Okay, so I mentioned gearing up, and I mentioned neurotransmitters. So when we look at methylation and how to support methylation, we're first of all looking at our ability to make SAMe. So SAMe, one of the things that it does is it helps make neurotransmitters such as dopamine and noradrenaline, and then that makes adrenaline. So these are all excitatory neurotransmitters. So if you have a client who is over methylating, then they could be making a lot of these neurotransmitters. If you have a client that is under methylating and you give them lots of methyl supplements, then you might actually overstimulate that person, so their neurotransmitter synthesis is increased so much they are creating far more dopamine and adrenaline, etc., than they really feel comfortable with, and in that case they might feel quite wired. So that is more likely to happen if they have SNPs on a COMT gene, and that's because the COMT gene supports neurotransmitter breakdown. So you can see on the left here, COMT needs to break down dopamine, and it needs to break down noradrenaline and adrenaline. It actually needs a little bit of methyl. It's an MT gene, so it does need SAMe to work properly. But sometimes the balance can get out. So if you've got someone with too much methyl or too much SAMe, it can stimulate the synthesis, but to a greater extent than supporting the COMT. So you get things out of balance. Now, to help COMT, magnesium is a cofactor, so that will help support the COMT gene in removing the dopamine and adrenaline. And variants on COMT, it's a very typical impact. They slow down that COMT activity. So this is a little summary, quite a busy slide again, but it's basically showing about balance of dopamine and adrenaline and the things that can impact it. So on the left-hand side, you can have SNPs on the MTRR gene and the MTHFR gene that lower methylation and lower the amount of methylfolate and methylcobalamin that is needed to support that and to support the dopamine and adrenaline. So you can put in more methylfolate, more methylcobalamin, more cofactors to support that activity. However, on the right-hand side, you can see a situation where we're explaining some of the things that can increase those neurotransmitter levels, like a slow COMT gene, like insufficient magnesium, and also environmental factors like cortisol, like caffeine, like sugar, which are also going to push dopamine and adrenaline. So the overall point here is that if you are thinking about methylation support, please don't just act on the back of an MTHFR SNP, because if you don't look at the other genes, if you don't look at the genes affecting B12 synthesis, then supporting with methylfolate might not make any difference. Alternatively, if you do put in a lot of methylfolate and a lot of methylcobalamin and you haven't looked at the COMT gene and you don't understand what's happening at the other end of the equation, you can send someone into an overstimulated state, and they will not thank you for that when they feel really, really wired, really jittery. And basically the things to look out for are similar symptoms to if someone had far too much caffeine. So it's about considering things in context, looking at other genes, looking at other substances, looking at the person's lifestyle and diet to see how they all interact. And this is a summary of that, really. So again, what are the needs of an individual for methylation support? Are they exceptional for any reason, such as pregnancy? Are they under a lot of stress? Do they have a high toxic load? Are they experiencing any symptoms of imbalance? And there's some of those there. What genes have you looked at and examined? Have you looked at all of them together and how they all collaborate and impact each other? And then from a testing perspective, what do you know about their nutrient status? You can do tests that quite easily look at B12, B6, folate through organic acid testing. You can also look at homocysteine and SAMe levels as well. So look at the big picture. Do not make assumptions based on one piece of information, because the risk is that you make someone feel worse rather than feel better. Okay, and these are some of the things that you can do to support it, but be very careful, particularly if someone does have a slow COMT gene. Introduce the support in a cautious, low and slow way, and think about the Bs in a complex, and think about other cofactors like zinc and magnesium as well, and also be aware of inhibitors like mercury and lead, and also ammonia, which disrupts methylation. Okay, so nearly finished. My advice would be to anyone considering genetic testing is don't treat it oversimplistically. It isn't that simple. It's just like all the things we've learned about nutrition. You get so much more from it when you understand the detail and you understand the bigger picture. So I encourage people to work with a trained professional who understands how to use genetic testing in context. And that context can include family history, health history, symptoms, looking at the gene to gene and gene to nutrient and inhibitor interactions, and also functional testing and how that all fits together. So all the things that you would look at as a nutritional therapist, but just putting genetics into that picture and including it as part of it is the appropriate way to use it. And that's why it's such a perfect fit to use Nutrigenomics in the context of a nutritional therapy, consultation or functional medicine practice, because it's at the heart of it, and it always has been, and it absolutely should be. Okay, so this is just a list of the LifeCode GX DNA tests and reports that we have. So we have a number of panels. You can find out about those on our website, and we've got sample reports on there as well. These are some of the things that make us different. We do take client identity and privacy very seriously. Data is protected, it's anonymised, it's never shared, and it is destroyed after 3 months. It's very accurate. If we can't be sure of a result, we don't report it. So we'd rather report a no call, no read than something that is potentially wrong. And most importantly, I think, are the next two things. So interpretation, it's evidence-based. We publish the research papers at the back of the reports, and there are hyperlinks to those papers. So all the statements that are made as to the effect of a SNP are evidenced and can be read and linked to in the report itself just by clicking on those links. And then finally, we really do believe in providing good, high quality, comprehensive practitioner support. So at the moment we do in-person seminars, and we provide one-to-one telephone support to run through results, and we are about to implement a whole range of other training, which is online and webinars and live case study things. So these are some of the resources that we use. You can look at that on the recording and click through to some of these things. They're all very reliable resources, including our own website. And this is some of the events that we've got coming up. So some day seminars and a retreat that are all approved by BANT. You can find out more on our website. And then finally, if you want to test with us and sign up with us, this is how you do it. So I think that's it from me, and I'm very happy to take questions.
Emma, thank you very much for that presentation. I certainly found it very interesting and useful, and it explains a lot of things to me, I'm sure to the other students as well. So thank you. Just a couple of questions. With regards to the clinician support, do you offer support for each profile that you have in the way that other labs do? Or is it more in the sense of training?
So we offer a range of support. So our training is organised according to our panels. So we offer a seminar on methylation, on detoxification, on female health and hormones, on brain health, for example. And then the other aspect of our support is the one-to-one telephone support. So when you get a test result through for a client, so the test result firstly goes to the practitioner directly and not to the client, but you can make an appointment with us to go through that individual result in detail and ask any questions, so we can focus on the things that are actually relevant to that person and make sure that you feel confident in interpreting it and confident in using it and getting the most for your client. And that's a really popular service that we provide, and the feedback that we get is that it's incredibly valuable.
That's great. Another question, I'm not sure if this is really relevant for you, but regarding vitamin D testing, if somebody has a SNP where they where their receptor is not working as well, how often do you recommend that they test if they're supplementing, and what are you aiming to achieve? What's the vitamin D level that you're aiming for?
So some people would recommend testing 4 times a year. It's entirely, it's a very individual thing in terms of practitioner approach. And I think I would also base that on symptoms. So, if someone is experiencing a lot of infections, if they've got low mood, or if they've got signs of osteoporosis, for example, then they would indicate to me that vitamin D might be a problem, and I would test more frequently. And I would always be aiming for a range. It depends on the scale that you're using, but to be at the top end of the vitamin D range, the more VDR SNPs that someone had. It's just important to maintain that. And, you know, basically people with those SNPs just can't get away with the vitamin D dipping as well as people without them. And one of the most frequently reported impacts is low mood and things like, especially in winter, SAD and around that. And it's just because the vitamin D is dipped, and it's probably dipped for 99% of the UK population, but people with VDR SNPs are less tolerant to that variation in level.
Great, thank you. Another question is, somebody's asking, so somebody just saying they recently did a 23andMe test. She didn't get the results yet, but she was asking whether you interpret other genetic testings, if they've done it through, for example, 23andMe.
We can interpret 23andMe to some extent, but unfortunately 23andMe don't test for all the things that we want to look at. So we don't recommend that as the ideal testing approach anymore. They used to test for a lot more than they do now, but they're an example of a company that started off looking at ancestry, and their range of SNPs, although it is big, doesn't necessarily cover all the SNPs that are of interest to a nutritional therapist. So, for example, a lot of SNPs involved in detoxification, and in particular hormone detoxification aren't included, and neurotransmitter breakdown as well is something that we wouldn't be able to get adequate information from a 23andMe result. I'd also be aware with 23andMe that they do share data with pharmaceutical companies. You can opt out of that, so please be aware that is the case, and if you want to opt out, make sure that you proactively do it, because the default is that it's shared. Some people aren't bothered about that, but some people are. And I think you certainly get some brownie points from letting your clients know that they've got that option.
Okay, great. Well, thank you very much. I'm just going to read the last comment by Charlotte, who said, fantastic webinar, thank you very much. And I agree with that as well. So I just wanted to give my final thanks to you, Emma, and thank you for finding time to speak to us. And is there anything else that you would like to add before we close?
Thank you very much, and please do come and visit us and contact us if there is anything we can do. We really welcome students to sign up with us, and we want to get you on board this exciting science and using it from day one. So please make the most of that.
Brilliant. Thank you. Oh, sorry. Yes, there is another question by Rory asking if the slides will be available, and like all the webinars, the slide and the recording is going to be available from the band website under the student sections. All the previous webinars are there as well, and this one should be there within a week. So thank you very much to everyone. I hope you enjoy the rest of the day, and Emma, thanks once again. Bye, everyone.
Thank you. Bye.